Hello everyone, welcome to my YouTube channel, Precision Manufacturing System. I'm back with another interesting video, and today in this video I'm going to talk about performing simulation with open source software, and to do that we need different software, using different software. For example, for if you want to do simulation in Abacus, since Abacus is a commercial software and it is so powerful, so you don't need to another software or another software to do I don't know, whatever. For example, an executable software or post or pre-processor software. But when we want to do a simulation with actually with an open source software, we need to some software for pre and post processor, and or maybe we need a software for executing and performing running our simulation, and maybe after that we need actually software for displaying the result. So today we want to talk about this kind of simulation. For example, how we can do the powder forming simulation with an open source software. As you know, powder forming simulation is so complex and difficult simulation, which is done by Abacus software, and actually it could be done with another other softwares. But in our channel we explain about this software and about how we can do this simulation with Abacus. But today I'm going to talk about new aspect of this simulation, and I want to show you guys how we can do this the powder forming simulation by actually open source software such as OpenRadioss or Ls-PrePost. So let's get started. But before starting the video, I really grateful if you could subscribe to my YouTube channel and keep with me until end of this video and hit the button, like button. Okay, let's get started. And as you know, for most of the actually open source software doesn't have drawing module like Abacus, and for that's why since the powder forming simulation is kind of so difficult and complex simulation, and its assembly takes a lot of time. For that's why I used a created model from the Abacus software and then imported to actually Ls-PrePost and do the all the rest of the simulation and defining a boundary condition and contact and whatever it might be and is needed for our simulation. I will do in Ls-PrePost and then run the simulation with OpenRadioss. So as you can see, we just node and element information and actually assembly model and assembly information of powder from in this file, which is created from Abacus, and we want to import this file in Ls-PrePost. Because we need an assembly model of actually powder and box for powder compaction. Also, the material property of contact is defined in Abacus software. Okay, this is our assembly model. Actually, you can do it in Ls-PrePost, but I want to use this file for my model. Let's open the Ls-PrePost software, and then open the IMP file. This one, share this. Okay. Okay, as you can see, the model is imported in Ls-PrePost, and we have an assembly model of powder and box, but we need to define our punch in this model. We have 385 powders, and as you can see, these are our parts model of 385 powders, and this is our punch. Let's remove the punch from it, and you can see the powder and its assembly. Also, we have actually surface and node information from this powder. Okay, let's do it and draw a punch. For creating a punch, we have to click on mesh and for node shell, and then by clicking on the top edge of the die, we can create our punch. And here we can increase the number of elements, and here we should write the punch actually a name. Here I want to assign the first part ID to our punch, and then create and accept. Done. Okay, then let's continue our simulation. Here we need to actually define the, we go to model module and keyword, and here we can actually create our rest of model. As you can see, we have here we have a step actually as we have in Abacus, but we need to define our step here. Here database, we can define our output, and actually here we can define material and other things. Okay, let's start and continue our simulation. First of all, I want to define the time step. Our time step is 4 seconds, and our actually minimum time step is 1 e minus 10, accept, done, and time step is 0.1. And since I just want to show the procedure. I want to I want use mass scale here, and I will put 1e-3 to do the simulation as fast as I can. So let's done, and then actually for in define and curve we can create our amplitude, and for defining the plastic material property you need to define curve in this section. So these information related to the plastic material property, and here I want to define the amplitude for movement and displacement, punch displacement. So here I will write the name, and here I have to select actually the number 1, actually 0, and then here I will put 0 0, and then 4 and 0 62 5 as a displacement insert. And please note that in Ls-PrePost we need to define an extra increment or extra second for amplitude. If we don't define this one, we will get the error. So we just define this the third row to solve this problem, and accept, and here done. And if you see the plot of this graph, as you can see, this is our displacement amplitude. Okay, then we need to define material. This material actually was defined by using and importing the IMP file, Abacus IMP file, but I want to define a rigid material for punch and die. For that's why we need to define this is material is for punch, a rigid punch, and this is the second ID. Here we have to input our density -12, and here E3, and then since we need to constraint apply in global direction, select 1, and we constrain our punch in X and Y displacement, so we have to click and put 4 here, and 7, as you can see, constrain X and Y and Z rotation, and here we have to set 7, and it's done for punch. Click accept, and another one, new ID, and here this is for die. All is same, just here since our die is completely fixed, it's fully fixed, for that's why we need to write 7, and here for box, and then accept, done. So then we have to define our material, define material to our parts, and before I want to create a shell section for actually punch and die. So edit, and here write shell section, and these are okay. As you can see, it should be for number 2, and this is number of actually shell integration point. I will put 3, and here we have to define our thickness, and then okay, accept, done. And then I have to go to parts and assign the created actually material to punch. Okay, here assign the material property shell section, down, and material rigid punch, done, accept, and then we need to define the same procedure for actually box. So we here and write die and put 2, again select shell section and material rigid die and accept, and done. Okay, now I want to define boundary condition. Our boundary condition just should be defined for punch, and since punch is rigid body, for that's why we need prescribed motion for rigid. So click on this one, edit, and ID1 and placement, and you should here define and select our body, and then here we have to select number 3. As you can see, Z translation DOF, and here we have to select number 2 displacement rigid body and nodes, and here we need to define amplitudes. So here we need to put minus, as we define our amplitude with positive number, but since we need to define we need to move our punch in Z direction downwards, so we need to put minus here and accept, done. And then after that I need to define general contact between these body. So I will use automatic general and just put part ID and static and dynamic friction coefficient 0.2, and just this, accept, done. And then let's see, we create boundary condition contact, we define our time step, and actually for data for output, we should define here our time step, and which it will actually export the animation output in every 0.1 second. Actually, it's somehow interval, so this is okay. And then in ASCII option, we need to define our actually output. What kind of output do we want to use and we want to see in our simulation? Since this is just tutorial simulation and I want to just show the procedure, I don't want to focus on this section. But if you want to see reaction force, you should actually select this one. And for displacement, let me see. Yeah, we should this one, select this one, put the interval, and then you need to, let me, not this one, actually this one for boundary condition. Just select and define the actually interval and accept done. Okay. For material we defined, and part we defined, section is defined, and just I need to define the keyword to define the number of processor, number of CPU. So here I will put 10, and then I think everything is defined, and the model is ready to run. Okay, done. And then I will save as the K file, put the K and write, for example, 385 powder, and save. Yes. Okay, it's save it. This is actually our K file, and if I open this K file, you can see this is the IMP file, which is created for running in actually OpenRadioss. OpenRadioss is open source software, and it mostly used for running, and it somehow is executable software. But if you are familiar with Linux environment, you can actually run and prepare your input file based on OpenRadioss template, and then run your simulation with OpenRadioss. So I will copy this K file, IMP file, and put it in my folder which was created in drive C, and then now I have to open the OpenRadioss executable software. So I will put the link for you guys for you guys to understand how and figure out how you can actually install and compile your OpenRadioss, and how you can work with this software. But in this video, I'm not going to talk about OpenRadioss and compiling and installing this software because it takes so long time. But I have to go to OpenRadioss and this script and open this software. Okay. Open. Open. Here we can define our number of processor, and at the end of the simulation we need to actually convert our model to anim VTK, which will be run with Paraview and create a CSV file. So by editing the job and click on edit job, the simulation will be started. It takes some time to actually run and read the file and run the simulation. So I will pause the video, and then after finishing the simulation I will actually show you guys the result of the simulation. And with Paraview, actually in OpenRadioss you cannot see the result. And also, since this software, the animation file, just as you can see, this is the VTK, and VTK just will be around with Paraview or maybe in some other actually software, but we cannot use this kind of format in Ls-PrePost. So if you want to do that and use Ls-PrePost for watching your simulation result, you should use Python code to convert the VTK to a 3D plot file. But at this time I just want to show the result of this simulation. Maybe in the next video I will show you guys how you can convert the VTK file to 3D plot file, and so that you can open your result in Ls-PrePost. I'm so sorry, in Ls-PrePost, and you don't need to another software such as Paraview to open your simulations result. So I will pause the video, and then after finishing the simulation I will back and show you guys the result. Just let's see the first increment. The simulation just started, as you can see. Okay, I will pause and come back again. Okay guys, our simulation was successfully done, as you can see, and the VTK files were converted and created actually, and then as you can see, the VTK files were created, and also the CSV file. CSV file includes some information about the simulation, and you can see you can open it in Excel file and see what kind of information of your simulation is stored in this file. And then at this time I want to show you guys the result. So open the Paraview software and open the actually our file, example new, and please know that you should open this file, this VTK file, to watch your simulation result. Click on apply. Okay, this is our model, and then I will remove the punch and die with threshold, and I have to select part ID and put 3, because 1 is punch, 2 is die, so lower threshold is 3, and the upper one is the last ID for particle, and then apply. Okay, let's have a with edge and see the last increment. Okay guys, as you can see, our model, our powders were compact, and our powder compaction simulation was successfully done, and you can use these series of actually simulation to run and perform your simulation if you don't want to use Abacus software, because Abacus is a commercial software and some guys maybe doesn't have access to this kind of software. But by this series of software, I mean, if you could actually create your node and your element of your actually create an assembly model of your simulation, you can do rest of the pre-processing of your simulation, such as defining boundary condition, contact, material, or whatever it might be needed for your simulation in pre-post, and then run your simulation with OpenRadioss, which is a strong software in compaction or crash problems. As you can see, this is our model and this is our result of compact powder forming simulation. Thank you so much for being with me until end of this video. If you found this video is helpful, please don't forget to subscribe to my YouTube channel and share this video with your friend, and please introduce our channel to your friend, because it could be a strong motivation for us to find a new method for you guys, and provide and prepare some more simulation or tutorial video for you guys. Thank you so much. See you guys. See you soon.